Hello everyone, welcome joining us in the low temperature thermochronology online lectures. Today, we'll be continuing with learning chapter 5. Last time, we have been learning section 1, fission track formation, and today we'll be going through section 2, fission track age calculation. Fission track dating relies on the same general equation as any radioactive decay scheme. It requires an estimate of the relative abundance of the parent and daughter product. For example, the number of uranium-238 and the number of spontaneous fission tracks per unit volume. Zeta is relatively straightforward. We count the number of spontaneous fission tracks on a given surface of mineral grain. It is started with mineral bedding, apatite in epoxy, and zircon in Teflon, followed by grading and polishing. Since latent fission tracks are generally only between 3 and 14 nanometers in width and can only be observed under a TEM, an etching process is used to review the tracks and make them visible under optical microscope with high magnification. Fission tracks in apatites can be selectively dissolved and enlarged by etching in dilute nitric acid, where zircon would require more rigorous conditions for etching. Finally, track density per known area is defined under a microscope and calculated. As is shown in the three pictures, fission tracks in different minerals appear to be quite different in terms of color, shape, and transparency. For the purpose of fission track dating, the concentration of uranium-238 in grains needs to be measured. The uranium-238 abundance is determined by, firstly, using a uranium-free mica as an external detector. Uranium-235 content is determined by irradiating the samples in a nuclear reactor with a relatively well-known dose of low-energy thermal neutrons. Higher energy neutrons induce unwanted fission of thorium-232 and uranium-238. During the irradiation, less abundant uranium-235 nuclei are artificially induced to undergo fission decay, producing a new set of tracks called induced tracks in the mica detector. After irradiation, mica is etched, enlarged, and induced tracks are reviewed and counted using microscopy in the same way as the spontaneous tracks are analyzed. Provided we monitor the thermal neutron flux, the number of induced tracks is indicative of the abundance of uranium-235. This value divided by the known natural uranium-235 and uranium-238 ratio determines the concentration of uranium-238. The fission track age is therefore determined by counting spontaneous and induced track numbers. This way of indirectly determination of uranium-238 concentration is called the external determining method, or EDM for short. Using an internal surface for recording spontaneous tracks and an external detector surface, usually a cleavaged sheet of low uranium muscovite for recording the induced tracks. One obvious advantage of EDM method is that it enables the dating of crystals individually. The analytical procedure of EDM method will be introduced in the third section of Chapter 6. The decay constant of fission in uranium-238 is not exactly known, and the determination of neutron fluence is problematic. Therefore, the Zeta calibration method is adopted, where standard samples with independently determined ages are irradiated together with other unknown samples. In this way, Each operator determines his or her own zeta calibration factor, and knowledge of the fission decay constant and irradiation flux is not needed. In practice, an individual analyst will undertake around 30 to 50 calibrations to determine their own particular zeta value for a given dosimeter. Thus, zeta also absorbs some of the vagaries of the observation process. The zeta age calibration approach was adopted to determine the fission track age. The general age equation of radiometric dating is this equation. The fission track age equation is a modified form of the above equation. Thermal neutron fluence has positive correlation with FT density induced by the neutron irradiation for a standard glass dosimeter, and this correlation is expressed here, where the constant B is the calibration factor, and its value is determined by an assumed value of spontaneous fission decay constant of uranium-238. The zeta calibration method allows the resolve of the still significant difficulties in determining thermal neutron fluence and the process value of lambda F and B separately. In the zeta approach, mineral age standards with independently determined ages are irradiated together with the unknown samples. This calibration and determination of zeta factor by an operator avoids the problematic uncertainties inherent in lambda F and B. Then, the FT-age equation becomes that is shown here. The symmetrical error of the FT single age determined using the EDM is given by the equation here. This error determination equation includes error on counting, standards, and the zeta calibration, and the typical error of FT ages is within 10% at a 1 sigma level. FT age is relatively low in precision, high in accuracy, which is the degree of conformity to true value. Typically, the fission track age is reported as some kind of average estimate of the individual, typically 20 to 40 single grain ages. There are three main ages estimates in common use: the main, the pooled, and the central ages. As the raw data are counts, for example, the number of induced and spontaneous tracks, then the appropriate probability distribution of the data is Poissonian. The pooled age is simply the sum of the spontaneous counts divided by the sum of these induced counts, while the mean age is the mean of the individual ratios of spontaneous to induced tracks. The latter has been used when the distribution of counts are inconstant with purely Poissonian variation, assessed with a conventional chi-square statistic. The central age is a more recent development and is essentially the weighted mean of log normal distribution of single grain ages. When the variation in the count population is constant with a Poisson distribution, and the value of probability of chi-square is larger than 5%, all dated grains are related to a single age, and then all three age estimates are essentially the same. Overall, the central age is the preferred sample age estimate, as it is more robust to outliers and non-Poissonian variations. The above is all for Section 2. Thank you for your attention.